Hi everyone, this is Professor Majumdar and you are watching ERUDIRE Plus, the professional CAD/CAM solution provider. Let's get started.
Hello viewers, today I'm going to show shear force and bending moment diagram of a cantilever beam subjected to some uniformly distributed load, by the same time some concentrated load also. Let us see the statement of the problem. A cantilever beam of span 1.5 meter is loaded as shown in figure. Draw the shear force and bending moment diagram of the beam using ANSYS mechanical APDL and compare the results. That means whatever results you will be getting from ANSYS mechanical APDL, that to be compared with the results obtained here itself. The length of the beam is total 1.5 meter, and from free end at a distance of 0.5 meter we are applying a uniformly distributed load with a span of 1 meter, and the load is 1 kilonewton per meter. And at the free end we are providing a concentrated point load of 2 kilonewton. Okay, so without wasting time, let us start our analysis using ANSYS mechanical APDL. Okay, first of all we need to create a directory, and in that directory we need to save everything. Next to that we need to change the title of this one, and let us change the title of this one as FEA 6. Okay, done. To see the title we need to click plot replot. It will show the title at the lower left corner. Next to that we need to select what type of analysis it is. It will be coming from preferences, and it is a static structural analysis. Okay, so structural analysis is checked in. Okay, next to that we need to provide elemental properties, and that will come from preprocessors. Element type, add, edit, delete. Let us add it, and we are providing beam with 3 defined strain, and element type reference number is 1. Okay, and from options we can select element behavior from linear to cubic form. Okay, done. Let us close it. Now we need to provide material properties. As we told before, material will be having modulus of elasticity of 2 into 10 to the 11 Newton per meter square and Poisson's ratio 0.3. So material models, structural, linear, elastic and isotropic, and we are providing modulus of elasticity as 2 if 11 and Poisson's ratio 0.3. Done. Let us close it. And sections, it is having a square cross section of breadth equal to 0.01 meter and height also 0.01 meter, right? So sections beam, common sections, and we are providing breadth equal to 0.01 meter and height also 0.01 meter. Okay, done. Now we need to start modeling, and from modeling we can create key points in active coordinate systems, and we know that total length of the beam is 1.5 meter. So let us start create model with the key points numbers. First key point will be created at origin, apply. Now second key point will be created at a distance of 1 meter from origin, apply, and the third one will be at a distance of 1.5 meter, apply. For providing orientation of the beam, let us provide a key point at a specific location. Let us provide the key point at a distance of x equal to 0 and y equal to -1. Okay, done. Now we need to join these key points in the form of lines that will be coming from lines, straight lines. Let us join key point 1 and key point 2. Done. Now key point 2 and 3 joined. Okay, done. Next to that we need to start meshing. Mesh attributes, and we need to consider the orientation key point also. So let us select all lines, and we are picking the orientation key point. Okay, let us select orientation key point 4 in this analysis. Okay, done. Now we can mesh it. First of all, it will be started with size controls, manual size, lines, all lines. Considering the elemental edge length for each line is equal to 10. That means we are dividing each line into 10 divisions. Okay, done. Now finally we can go for meshing. So mesh, lines, pick all, meshing is complete. Now we need to apply our boundary conditions, and that will be started with loads. Analysis type, it is a static structural analysis. So new analysis, static structural analysis. Okay, done. Now define loads. As it is a simply supported beam, so the left hand side will be completely fixed. So define loads, apply. Let us select key point 1. Okay, and it will be all degrees of freedom. Okay, done. So left hand side is completely fixed. Now we need to apply our loading. For applying loading, let us plot the lines to see the specific locations, right? Okay, now the thing is, from left hand side, for a span of 1 meter we need to apply a uniformly distributed load of 1 kilonewton per meter. Okay, so define loads, apply, and it will be pressure on beams. Let us select with box selected. Okay, and the load is 1 kilonewton per meter. In the downward direction, so it is minus, and finishing also it will be the same number, minus 1000. Okay, so we have applied a load of 1 kilonewton at the starting node and with a span of 1 meter, and finally at free end we need to apply 1 point load. At the extreme right hand side we need to apply point load of 2 kilonewton, right? So force moment on key points, let us select the extreme right hand side key point. Okay, and it will be in the y direction, it is 2 kilonewton. In the negative direction of y it will be minus 2000 newton. Okay, done. We applied all our boundary conditions. Now we need to solve it, right? For solving we need to start with solution. Solve current ls. If everything is right, it will show solution is done. Okay, let us see it. It is showing solution is done, so everything is perfect. We can see your results from general post processing. Okay, right, let us close it. And first of all we need to read results from general post processing. So read results, and let us read the last set. Done. Next to that we need to create element table. Starting from element table, define table, we need to add it, and we know that for seeing the shear force and bending moment diagram we need to depend on different numbers. For bending moment it will be SMIS 2 and 15. So by sequence number SMIS 2, apply, again repeat the process, select by sequence number and SMIS 15. These two numbers are actually for bending moment, apply, done. Next one we need to see the shear force, again repeat the process by sequence number SMIS 5, apply, and the last one for shear force it will be again by sequence number and SMIS 18. Okay, done. So we selected all the specific numbers, SMIS 2 and 15 for bending moment and SMIS 5 and 18 for shear force. Okay, let us close it. Now first of all we'll see the results from listing. So list results, we want to see reaction solution, right? All items. You can see that maximum reaction is 3000 newton at node number 1 in y direction, right? Okay, now we need to see the results of shear force and bending moment together from list results. So element table data, and let us select all the numbers SMIS 2 and 15 for bending moment and SMIS 5 and 18 for shear force. We'll see all these results together. Okay, see, first and second column represents bending moment at a specific nodes, and third and fourth column represents shear force at a specific nodes, right? We are having total 20 nodes, and each node we are having shear force and bending moment, right? Let us see at the last moment. You can see here that maximum bending moment occurs at node number 20. It is 100 Newton meter. It is not maximum, it is the minimum one because the sign is negative. And you can see shear force. Maximum shear force is occurring at node number 1. It is 3000 Newton. Okay, let us close this one. Now we'll see the results in the form of graph, right? So plot results, contour plot, line elemental response, and let us select elemental response numbers SMIS 2 and 15 for bending moment. Okay, right. So this is representing bending moment diagram for this specific beam with uniformly distributed load and concentrated load on a cantilever beam. And you can see here maximum bending moment occurs at node number 1. It is minus 3500 Newton meter. And let us see the question also. See here, maximum is 3.5 kilonewton meter occurring at node number 1. So it is exactly same what we saw in our ANSYS mechanical APDL. It is 3.5 kilonewton meter. Here it is, you can see minus 3.5 kilonewton meter or minus 3500 Newton meter at node number 1. It is exactly same what we saw in our theoretical results. Next to that, we will see our shear force diagram. So line elemental response, and we will see numbers SMIS 5 and SMIS 18 that will represent shear force diagram. Okay, it is showing this one that maximum shear force is occurring at node number 1. It is 3000 Newton and minimum is 2000, right? Let us see the drawing from our question paper itself. Let us see that it is showing maximum shear force is 3000 Newton and minimum is 2000 Newton. Okay, So it is actually validating our results. It is exactly same what we saw in our question paper. Okay, let us close this one. Now we'll do another thing. That means we want to see the animation of this beam. For that, first of all, we need to see the element, and that to be converted into 3D, right? For converting this one into 3D, we need to start with style and size and shape, and display of element should be on. Let us make it on. Okay, now you can see this is the model, this is the beam. We can see this one from oblique view to have a better representation. This is the beam, right? Now we want to see the animation of this beam. So plot controls, animate, and we want to see deform results. Let us see the deformation along y direction. Okay, let us change the dilapidated to less numbers. See how this beam will be vibrating by the application of concentrated load and also uniformly distributed load. Okay, let us close this one. So this is all about our today's video. This was a very simple analysis of a cantilever beam under uniformly distributed load and also a concentrated load, right? And we saw that the result obtained through ANSYS mechanical APDL is exactly same what we got in our question paper. So this is validating our results. Okay, so thank you so much for watching this video. Thank you again. Bye.
If you like this video, please subscribe and share. And if you have any kind of doubts, please write to me. Thank you so much for watching this video. Thank you again. Bye.